Welcome to the Launchpad. Think of your upcoming Cambridge physics exam, specifically the 9702 syllabus, like a high-stakes space mission. There is absolutely zero margin for error. Every single calculation, every single definition must be perfect for a successful launch. Welcome to this explainer where we are going to uncover the invisible architecture of magnetic fields, discover exactly how they create physical force, and most importantly, show you exactly how to secure maximum marks when you are tested on it. If you have ever wondered how an invisible field can physically push or pull an object in the real world and how to articulate that perfectly to an examiner, you are in the right place. We're going to break down the science, the equations, and the sheer power of electromagnetism while dodging the traps that catch out thousands of students every single year. Let's get started. Here is our flight plan for today's mission. We are going to build your understanding step by step, starting with a classic exam context. First, we'll look at the 1820 compass discovery. Second, we are defining the motor effect. Third, we'll master Fleming's left-hand rule. Fourth, we'll decode the force equation. And fifth, we'll wrap up by defining the Tesla. By the end of this, you won't just understand the motor effect. You'll have a foolproof strategy for predicting force, unpacking core equations, and racking up those A-star marks. Section 1. The 1820 compass discovery. Let's dive right into Act 1, the challenge. I want you to imagine you open your exam paper and you see a 4-mark question about the historical origins of electromagnetism. Now let's look at two hypothetical students taking this exam. We'll call them Alex and Sam. The question asks them to explain the significance of the 1820 compass discovery. Look at the split screen in your mind right now. Alex writes a massive paragraph. Alex is overloading the page with raw physics facts about this guy on screen, Danish physicist Hans Christian Ørsted. Alex writes about how Ørsted accidentally noticed a compass needle deflecting near a wire carrying a current. But Alex doesn't actually answer the command word. Sam, on the other hand, just rushes and writes, "Wires make magnets," completely missing the necessary technical terms. Both of them just lost massive marks. What the examiner is actually looking for is the analysis. Ørsted's discovery proved, for the absolute first time, that electric currents actively produce magnetic fields. It's not just a fun trivia fact, it's the foundational bridge between electricity and magnetism. This brings us to a strict, non-negotiable Cambridge definition. If you are asked to define a magnetic field, do not write the area around a magnet. You will get 0 marks. Look at the definition on screen. A magnetic field is specifically a region of space where a force is experienced either by moving charges or by permanent magnets. Notice the precision? Moving charges, permanent magnets. It's an invisible arena where magnetic forces are active. If you memorize this exact phrasing, that is a guaranteed mark in the bank. No fluff, just pure examiner-approved precision. Section 2, defining the motor effect. Okay, we've set the baseline. Now let's look at what actually happens when multiple magnetic fields meet inside that arena, and I'm going to reveal the ultimate exam strategy framework. Picture a classic exam paper diagram. We have an experimental setup. Imagine placing a loose strip of aluminum foil directly between the north and south poles of a standard horseshoe magnet. Crucially, and this is a word you must highlight in any exam question, the foil is placed at a strict right angle to the magnetic field lines running between those poles. So here is the question that trips up so many candidates. What exactly happens when the current is switched on and these two magnetic fields interact? Remember, Ørsted proved the current creates its own magnetic field. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, back to the foil and the magnet. How do we structure the perfect answer to this interaction? We use the Peel framework. Point, evidence, explanation, link. Let's apply Peel right now. Point. The foil physically jumps and becomes taut. Evidence. This occurs because an electrical current is flowing through the conductor. Explanation. The magnetic field of the live wire interacts with the existing field of the permanent horseshoe magnet, creating a physical push. Link. This phenomenon of an electromagnetic force acting upon a current-carrying conductor in a magnetic field is called the motor effect. Boom. Full marks. Notice how we didn't just dump facts like Alex, and we didn't rush like Sam. We provided a structured, logical sequence. The motor effect is literally the fundamental principle behind how electric motors work, and now you know how to articulate it perfectly. Section 3, Fleming's left-hand rule.
We know the foil jumps, but examiners love to ask you to predict which way it will jump. This brilliantly illustrates how we can determine the exact direction of that physical force without just guessing.
This is where the transformation happens. I want you to literally hold up your left hand right now at your screen. Seriously, do it. Arrange your thumb, your first finger, and your second finger so they are all at strict right angles to one another. You're forming a 3D corner. If we look at Alex and Sam's past papers, they usually mix up which finger means what, and you'll see a sea of red pen marks on their exams. Let's transform those red marks into green check marks right now. Here is your physics success blueprint for Fleming's left-hand rule. Memorize this trick. The thumb points to the motion, or the resulting force. Notice the M in thumb in motion. Your first finger points to the magnetic field. F for first, F for field. And your second finger indicates the direction of the conventional current. C for second, C for current. By aligning your first two fingers with the field from north to south and the conventional current from positive to negative, your thumb will automatically reveal exactly which way that aluminum foil is going to jump. It's a physical cheat code built right into your hand. Section 4, the force equation. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never missed our weekly exam strategy sessions. All right, let's move from the physical to the mathematical. Welcome to the interactive workshop segment. We have a 60-second data scan challenge. Look at the variables on screen. Experiments show electromagnetic force, F, is proportional to 3 things. Current, I, length of the conductor in the field, L, and the sign of the angle between the conductor and field direction, sine theta. When you are given a complex data table in an exam, you need to quickly scan and extract the core trend. What's the trend here? If you increase the current, the force increases. If you increase the length of the wire inside the field, the force increases. They are directly proportional. Now for challenge 2, find the flaw. I'm going to show you a flawed statement, and you have 30 seconds to figure out why it loses marks. Here's the equation. F equals B times I times L times sine theta. Now here's a student's answer. The force on a wire is just the magnetic strength times the current times the length. Did you catch the flaw? The student completely ignored the angle. B is our constant for magnetic flux density, depending on the magnet strength, but B sine theta represents the exact component of the magnetic field that is at a pure right angle to the conductor. You cannot ignore sine theta. That is an examiner commentary staple. Students drop marks because they forget the geometry of the setup. Time for challenge 3, speed writing. You have 30 seconds to explain this specific edge case. What happens if the wire happens to run completely parallel to the magnetic field? Your perfect peel paragraph should look like this. Point, there is absolutely no force exerted on the conductor. Evidence, the angle theta between the wire and the field is 0. Explanation, according to the equation, sine of 0 equals 0, which zeroes out the entire calculation. Link, therefore parallel fields produce 0 electromagnetic force. If you can write that concisely under pressure, you are performing at an A-star level. Section 5, defining the Tesla. We are entering Act 5, the final system. Now that we have our force equation, we finally have the tools to precisely define that mysterious constant B, which physicists formally call magnetic flux density. One of the 3 rules that guarantee top marks is command word decoding. When a question says derive or show that, this is what you do. By simply rearranging our force equation, isolating B, we get B equals F divided by the product of I, L, and sine theta. This clearly shows an examiner that magnetic flux density is mathematically equal to the force per unit current per unit length acting on a straight perpendicular wire. You are proving the concept using algebra, leaving no room for argument. And this brings us to the ultimate definition to commit to memory. 1 Tesla, represented by a capital T, what is it? It is the uniform magnetic flux density, which causes a force of exactly 1 Newton per meter on a long straight wire carrying 1 ampere of current. This is the gold standard, textbook perfect response. If you write this exact sentence in your exam, you secure full marks for the definition. No overloading, no rushing, just precision. Let's add this to your mental cheat sheet. Because physics is the absolute science of measurement, Cambridge examiners love multiple choice questions that test unit equivalence. It is incredibly useful to know that a single Tesla can also be perfectly expressed as Webers per square meter, or WB(m to the minus 2. And, stemming directly from our rearranged equation, it can also be expressed as newtons per meter per amp, or Nm to the minus 1 a to the minus 1. Recognizing these alternative expressions will save you massive amounts of time on paper 1. Let's put some real-world scale to this, because examiners love context questions. A whole Tesla is actually a massive unit. An MRI machine might use a few Teslas. But the Earth's entire magnetic flux density in the UK is only about 44 microteslas, acting at a 66-degree angle to the horizontal. Notice the unit prefix there? Micro. 10 to the power of -6. Don't let prefixes trip up your calculator work. Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. As we wrap up this explainer, I'll leave you with this final thought. If a tiny 44 microtesla field is enough to steer a compass and guide global navigation, what other powerful unseen fields are silently shaping our universe? The motor effect is just the beginning of your mastery. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Subscribe right now to @Ace the Exams IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.